Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day climbing your own metaphorical mountains, or perhaps you're simply the kind of person who finds peace in pondering the ancient forces that shape our world. Either way, you're in the right place. Tonight's journey will take us deep into one of Earth's most spectacular phenomena, the formation of mountains themselves. You've got nothing to do but rest. Let your breathing slow and your mind drift through geological time. Let the weight of the day lift as we explore forces so vast they crumple continents, and processes so patient they measure change in millions of years. Because tonight, we're not just looking at mountains. We're traveling through the very mechanisms that thrust stone kilometers into the sky, that fold solid rock like fabric, and that transform the face of our planet generation after generation. The mountains you see today, whether they're the snow-capped peaks of the Himalayas, the volcanic sentinels of the Pacific Northwest, or the ancient worn hills of the Appalachians, each one tells a story. A story written in layers of rock, carved by time, and driven by forces that operate beneath our feet every single moment. Some mountains are being born right now, growing imperceptibly year by year. Others have stood for hundreds of millions of years, slowly surrendering to gravity and weather, their peaks diminishing grain by grain into the sea. We'll journey from the molten depths where continents drift on a sea of partially melted rock, to the highest summits where ice and wind sculpt stone. We'll witness collisions that last tens of millions of years, eruptions that build mountains in mere centuries, and fractures that split the land itself. You will learn how mountains can form without a single volcano, how some peaks are actually the roots of far more ancient ranges, and why the mountains you're familiar with might one day vanish completely, only to be replaced by new ranges yet unborn. And before we begin, if these calm explorations help you unwind or offer you a peaceful way to end your day, consider liking this video and subscribing to the channel. It helps other curious minds find their way here too, one sleepy soul at a time, seeking wonder before rest. Now, settle in. Let your thoughts quiet. And let's begin our descent into deep time, where mountains are not permanent fixtures but fleeting expressions of a restless, living planet. The restless Earth, understanding plate tectonics. To understand how mountains form, we must first understand that the ground beneath your feet is not as solid or permanent as it seems. You live on a planet whose surface is broken into enormous pieces, massive slabs of rock called tectonic plates that drift across the face of Earth like rafts on an impossibly slow sea. This movement, this perpetual migration of continents and ocean floors, is the foundation of nearly every mountain range that has ever existed. Picture Earth as a layered sphere. At the very center lies the inner core, a solid ball of iron and nickel subjected to such immense pressure that despite temperatures reaching over 5,000 degrees Celsius, it remains frozen solid. Surrounding this is the outer core, a liquid metal ocean that generates Earth's magnetic field as it swirls and flows. Above this lies the mantle, a vast region of hot, dense rock that makes up the majority of our planet's volume. The mantle is not quite solid and not quite liquid. It exists in a state geologists call plastic or ductile. Over human timescales, it seems solid as stone. But over geological time, spanning thousands and millions of years, it flows like an incredibly viscous fluid, moving perhaps a few centimeters per year. Think of it as similar to cold honey or warm glass, materials that appear solid but will slowly deform and flow when subjected to pressure over long periods. This flowing mantle is driven by heat. Deep within Earth, heat generated by radioactive decay and leftover warmth from the planet's formation creates convection currents, great circular flows of rock that rise where hot and sink where cool. These currents are the engine that drives everything at the surface. They are what cause continents to drift, oceans to open and close, and mountains to rise. The outermost layer of Earth, the lithosphere, consists of the crust and the uppermost part of the mantle, cooled and rigid enough to fracture rather than flow. This lithosphere is broken into about 15 major plates and dozens of smaller ones. These plates vary tremendously in character. Some are made primarily of thick, light continental crust, composed mainly of rocks like granite that are rich in silicon, aluminum, and oxygen. Others consist mainly of thin, dense oceanic crust, formed from dark basaltic rocks rich in iron and magnesium. Most plates contain portions of both types. These plates are in constant motion, driven by those deep mantle currents below. They move at rates comparable to the growth of your fingernails, typically between 1 and 10 centimeters per year. This might seem trivially slow, but multiply those centimeters by millions of years, and you have plates traveling thousands of kilometers, oceans opening where none existed before, and continents colliding with planet-altering consequences. The boundaries between plates are where the action happens. There are 3 main types of plate boundaries, each creating different features and, crucially for our story, different types of mountains. Divergent boundaries occur where plates pull apart, where new crust forms as magma rises from below to fill the gap. Mid-ocean ridges, those great underwater mountain chains that wind through every ocean basin, form at divergent boundaries. Iceland sits atop one such ridge, where the mid-Atlantic ridge rises above sea level, creating a landscape of volcanic fissures and geothermal activity. Convergent boundaries are where plates move toward each other, colliding in slow-motion impacts that can last tens of millions of years. What happens at a convergent boundary depends on what types of crust are colliding. When an oceanic plate meets a continental plate, the denser oceanic plate usually slides beneath the lighter continental plate in a process called subduction. This creates deep ocean trenches and, crucially, volcanic mountain ranges on the overriding plate. When 2 continental plates collide, neither can easily subduct because both are too light and buoyant. Instead, they crumple together, their edges thickening and rising to form immense fold mountain ranges. Transform boundaries occur where plates slide horizontally past each other, grinding and lurching along faults like the San Andreas in California. While these boundaries don't typically form major mountain ranges, localized compression at bends in the fault can push up smaller mountain blocks. Understanding these plate boundaries is essential because nearly every major mountain range on Earth can be traced back to the interactions occurring at these boundaries. The Andes Mountains, rising along South America's western coast, formed where the oceanic Nazca Plate subducts beneath the South American Plate. The Himalayas, Earth's highest mountains, rose from the ongoing collision between the Indian and Eurasian plates. The East African Rift Mountains are forming where the African continent is slowly tearing itself apart along a divergent boundary. The discovery of plate tectonics in the mid-20th century revolutionized geology. Before this understanding, the presence of marine fossils on the mountain summits was mysterious. How could sea creatures end up kilometers above sea level? Some early explanations invoked biblical floods or suggested the fossils had somehow grown in the rocks. But plate tectonics provided the answer. Those rocks were formed beneath ancient seas and were later uplifted as plates collided and mountains rose. The fossils are passengers on a journey from seafloor to summit, crustal fragments lifted by the slow but irresistible force of colliding continents. This restless nature of our planet, this constant motion of plates driven by heat from Earth's interior, this is the great stage upon which the drama of the mountain formation plays out. Mountains are not simply there, fixed and eternal. They are the temporary expressions of these ongoing plate movements, features that rise when plates collide or when magma breaks through to the surface, features that will eventually erode away as weather and time work their patient dissolution. But before that distant future, before erosion wins its slow victory, mountains stand as monuments to the immense forces operating within our living planet. With this foundation laid, with an understanding of the engine that drives change at Earth's surface, we can now turn to specific mechanisms of mountain building, beginning with, perhaps the most spectacular, the collision of continents. Fold mountains, when continents collide. Imagine two enormous rafts of continent-sized rock, each thousands of kilometers across and dozens of kilometers thick, drifting across Earth's surface. Now imagine them colliding, not with the sudden violence of cars crashing, but with a slow, inexorable pressure that persists for millions upon millions of years. The edges of these continents cannot pass through each other, cannot slide past each other, and, because both are too light and buoyant to sink into the denser mantle below, they cannot easily dive beneath each other either. So they do the only thing they can. They crumple, they fold, they thicken, and in doing so, they rise. This is how fold mountains form, and it is the mechanism behind some of Earth's most impressive mountain ranges. The process is called orogeny, from ancient Greek words meaning mountain birth, and it represents one of the most dramatic expressions of plate tectonics visible at Earth's surface. Let us travel to the most iconic example, the Himalayan mountain range, which includes Mount Everest, Earth's highest peak at 8,949 meters above sea level. The Himalayas are young mountains, geologically speaking. Their story begins around 50 million years ago, though the setup occurred much earlier. At that time, India was not attached to Asia as it is today. Instead, India was an island continent, separated from Asia by an ancient ocean called the Tethys Sea. But India was moving, Driven by the spreading of new oceanic crust at a mid-ocean ridge to its south, the Indian plate was drifting northward at speeds that, for tectonic plates, were remarkably fast, perhaps 15 or more centimeters per year. The ocean floor of the Tethys Sea, lying between India and Asia, was being consumed in a subduction zone along Asia's southern edge. As oceanic crust subducted, the Tethys Ocean gradually closed, and India drew closer to Asia. Eventually, around 50 to 55 million years ago, the moment of a contact arrived. The leading edge of the Indian continent began to collide with the southern edge of Asia. Unlike the oceanic crust that had been subducting before, continental crust is too light, too buoyant to be easily dragged down into the mantle. The collision slowed but did not stop. India continued pushing northward, and the two land masses began to merge. What happened next is almost difficult to comprehend in its scale. The edges of both continents began to crumple and fold. Horizontal layers of sedimentary rock that had accumulated over hundreds of millions of years on ancient seafloors and continental margins were compressed. The pressure was immense and unrelenting. Rocks that had lain flat were bent into enormous folds, some spanning tens of kilometers. In many cases, the rock layers snapped entirely, creating thrust faults where older layers of rock rode up and over younger layers, stacking the crust in great sheets called napes. As the collision continued, the crust didn't just fold horizontally, it thickened vertically. Imagine taking a soft clay slab and pushing the ends toward each other. The clay doesn't just compress, it bulges upward. Continental crust behaves similarly, though over vastly longer timescales. As India's relentless northward motion continued, the crust at the collision zone thickened from a normal continental thickness of around 35 to 40 kilometers to as much as 70 or even 80 kilometers beneath parts of the Tibetan Plateau. This thickening is crucial to understanding why mountains rise. Earth's crust floats on the denser mantle below, much like ice floats in water, through a principle called isostasy. When crust thickens, it becomes more buoyant, and it rises. The thicker the crust, the higher the surface elevation. This is why the Tibetan Plateau, with its enormously thick crust, sits at an average elevation of over 4,500 meters, and why the Himalayan peaks, formed along the southern edge of this thickened zone, reach above 8,000 meters. But the process is not simple or smooth. The collision generates enormous internal stresses in the rocks. Deep within the forming mountain range, where temperatures and pressures are extreme, the rocks undergo metamorphism. Original sedimentary and igneous rocks are transformed into new forms. Shale becomes slate, then schist, then gneiss. Limestone transforms into marble. These metamorphic rocks, formed in the hot, compressed core of the mountain range, are later exposed at the surface as erosion strips away the overlying material, providing direct evidence of the depths to which rocks were buried during collision. The Himalayas continue to rise today. GPS measurements show that parts of the range are still being uplifted at rates of several millimeters per year. This might not sound impressive, but over 1 million years, that's several kilometers of elevation gain, assuming erosion doesn't remove the material just as fast as it rises. The Indian plate continues to push northward at about 40 to 50 millimeters per year, though much of this motion is now accommodated by the continued thickening of the Tibetan Plateau and by earthquakes throughout the region. The Himalayas are not unique. Other spectacular fold mountain ranges formed through similar continental collisions. The Alps, that great arc of mountains spanning Central Europe, formed from the collision of the African and Eurasian plates beginning around 65 million years ago. Like the Himalayas, the Alps contain intensely folded and faulted rocks, with nappies that have been transported tens of kilometers from their original positions. The Appalachian Mountains in eastern North America, now ancient and worn, tell a similar story from much deeper in Earth's past. These mountains formed primarily during a collision between ancestral North America and ancestral Africa, part of the assembly of the supercontinent Pangaea around 300 million years ago. At their peak, the Appalachians may have rivaled the modern Himalayas in height, but time has worn them down. Hundreds of millions of years of erosion have reduced peaks that might once have soared above 6,000 meters to summits that now rarely exceed 2,000 meters. Yet the structure remains. The folded and faulted rocks bearing witness to ancient collisions. The Zagros Mountains in Iran, the Atlas Mountains in North Africa, the mountains of New Guinea, all are fold mountains formed where continents or smaller continental fragments collided. Each range has its own specific history, its own timing, its own details of collision, but all share the fundamental mechanism: compression leading to folding and thickening of the crust, which leads to uplift and the rise of mountains. The timescales involved in creating fold mountains are vast. From the initial collision to the development of a mature mountain range takes tens of millions of years. The mountains then persist for tens or even hundreds of millions of years more as erosion slowly wears them down. Eventually, given enough time, even the mightiest mountains are reduced to nothing more than gentle hills or broad plains, their rocks distributed across the continents and ocean floors by rivers, glaciers, and wind. But during their prime, fold mountains are among Earth's most spectacular features. They create barriers that alter climate patterns, forcing moisture-laden winds to rise and cool, dropping their water as snow and rain on windward slopes while leaving leeward regions in rain shadows. They provide habitats for unique ecosystems adapted to high-altitude conditions. They serve as water towers, storing precipitation as snow and ice that feeds rivers during dry seasons. And they inspire awe in all who see them, standing as visible proof of the immense forces operating deep within our planet. As we leave the realm of fold mountains, formed from the slow collision of continents, we turn now to a very different mechanism of mountain building, one involving not compression but heat, not folding but eruption. We turn to volcanic mountains. Volcanic mountains, born from fire. While fold mountains rise from the compression of colliding continents, volcanic mountains are born from below, built layer by layer from molten rock that has journeyed from deep within Earth to erupt at the surface. These mountains form not through the folding and thickening of existing crust, but through the addition of new material, lava and ash, accumulating over countless eruptions to construct edifices that can rival or exceed fold mountains in height. The story of volcanic mountains begins with magma, molten rock residing in chambers beneath Earth's surface. This magma forms when conditions of temperature, pressure, and water content allow rock to melt. The specific conditions vary, but most magma originates either in the mantle, that hot layer beneath the crust, or in the crust itself when conditions become sufficiently extreme. Once formed magma is less dense than the solid rock surrounding it, so it tends to rise, working its way upward through cracks and zones of weakness until it either solidifies underground to form plutonic rocks or reaches the surface to erupt as a volcano. Not all volcanic eruptions build mountains. Fissure eruptions, where lava pours from long cracks in the ground, can create extensive lava fields or plateaus but typically don't form prominent peaks. To build a mountain, eruptions need to occur at a relatively localized vent or cluster of vents, allowing material to accumulate in one place rather than spreading far and wide. When this happens repeatedly over thousands or millions of years, a volcanic mountain is born. There are two principal types of volcanic mountains, and they differ dramatically in both appearance and behavior. The first type, shield volcanoes, are built almost entirely from layers of fluid lava. Picture a warrior's shield lying on the ground, broad and gently sloping. That's the profile of a shield volcano, with slopes that typically rise at angles of only 5 to 10 degrees. These gentle slopes are a direct consequence of the lava's properties. The lava that builds shield volcanoes is basaltic, dark in color, and relatively low in silica content, which makes it hot and fluid. When this lava erupts, it flows easily, sometimes traveling many kilometers from the vent before cooling and solidifying. The Hawaiian Islands provide the most famous examples of shield volcanoes. The entire island chain sits above a hotspot, a plume of abnormally hot rock rising from deep within the mantle, possibly from as deep as the core mantle boundary nearly 3,000 kilometers below the surface. As the Pacific Plate slowly moves northwest, this stationary hotspot burns through it like a blowtorch through sheet metal, creating a trail of volcanic islands. Each island formed as it passed over the hotspot, then slowly moved away as new islands formed in its place. Mauna Loa on the Big Island of Hawaii is Earth's largest active volcano in terms of volume, containing approximately 75,000 cubic kilometers of rock. From its base on the ocean floor to its summit, it rises more than 9,000 meters, taller than Mount Everest when measured from base to peak, though much of it lies underwater. Mauna Loa doesn't look particularly impressive from a distance. Its slopes are gentle, almost benign, but this is deceptive. The volcano is immense, and it grew to this size through countless effusive eruptions over the past 700,000 years or so, each eruption adding another layer of basaltic lava to the growing edifice. Shield volcano eruptions are generally not explosive. The fluid lava allows volcanic gases to escape relatively easily, so pressure doesn't build to catastrophic levels. Instead, eruptions typically feature lava fountains, curtains of fire where molten rock is hurled tens or even hundreds of meters into the air, but in a way that is more spectacle than danger. The lava then flows downslope as glowing rivers, gradually cooling and solidifying. These eruptions can continue for weeks, months, or even years, steadily adding to the volcano's bulk. The second major type of volcanic mountain is the stratovolcano, also called a composite volcano. These are the classic cone-shaped volcanic peaks that come to mind when most people think of volcanoes. Mount Fuji in Japan, Mount Rainier in Washington, Mount Vesuvius in Italy. Stratovolcanoes are steeper than shield volcanoes, with slopes that can reach 30 to 40 degrees near the summit, giving them their iconic conical profile. The difference in shape reflects a difference in composition and eruption style. Stratovolcanoes are built from a mixture of lava flows and pyroclastic materials, fragmented rock, ash, and pumice ejected during explosive eruptions. The lava that erupts from stratovolcanoes is typically andesitic, or even more silica-rich, making it more viscous than the basalt of shield volcanoes. This sticky lava doesn't flow far from the vent before solidifying, creating steeper slopes. More importantly, the high viscosity traps volcanic gases in the magma, building pressure until it is released explosively. Most stratovolcanoes form at subduction zones, those convergent plate boundaries where oceanic crust descends into the mantle. As the subducting slab sinks, it carries with it water trapped in minerals and sediments. As the slab descends into increasingly hot regions, this water is released and rises into the overlying mantle wedge, lowering the melting point of the mantle rock and causing it to partially melt. This produces magma that is more evolved, more silica-rich than the basalt produced at mid-ocean ridges, and this magma rises to feed the volcanoes at the surface. The result is volcanic mountain chains paralleling the subduction zones. The Andes Mountains along South America's western coast are perhaps the most spectacular example. Stretching over 7,000 kilometers and containing numerous towering stratovolcanoes. Some, like Ojos del Salado on the Argentina-Chile border, exceed 6,800 meters in elevation, making them among the highest mountains on Earth. The Cascade Range in the Pacific Northwest of North America is another example. A chain of stratovolcanoes, including Mount Rainier, Mount Hood, and the infamous Mount St. Helens, which erupted catastrophically in 1980. The explosive nature of stratovolcano eruptions makes them among Earth's most dangerous geological phenomena. When pressure finally overcomes the strength of the rocks sealing the magma chamber, the result can be devastating. The 1980 Mount St. Helens eruption removed the volcano's entire north face in a lateral blast, sent an ash column 24 kilometers into the atmosphere, and triggered massive lahars, volcanic mud flows that buried valleys beneath tens of meters of debris. The 1991 eruption of Mount Pinatubo in the Philippines ejected so much ash and sulfur dioxide into the stratosphere that it measurably cooled global temperatures for several years. Yet, between these catastrophic events, stratovolcanoes can lie dormant for decades, centuries, or even millennia, giving a false sense of security. The town of Pompeii, famously buried by the eruption of Mount Vesuvius in 79 AD, had largely forgotten that Vesuvius was a volcano. The mountain had been quiet for so long that it was simply part of the landscape, until it awoke with terrible suddenness. A third setting for volcanic mountain formation is along rift zones, where continents are pulling apart. As the crust stretches and thins, pressure on the underlying mantle decreases, causing it to partially melt through a process called decompression melting. The resulting magma rises through the fracturing crust to create volcanic mountains. The East African Rift provides excellent examples, including Mount Kilimanjaro, Africa's highest peak at 5,095 meters, and Mount Kenya. These are stratovolcanoes, but they formed in a different tectonic setting than the Andes or Cascades, associated with extensional rather than compressional forces. Iceland, sitting atop the mid-Atlantic ridge, represents rifting in an oceanic setting. Here, volcanic activity is frequent and diverse, building shield volcanoes, creating fissure eruptions, and constructing stratovolcanoes. The entire island is volcanic, constantly being rebuilt by eruptions as it rides the divergent boundary between the North American and Eurasian plates. Volcanic mountains, regardless of type or tectonic setting, are transient features on geological timescales. They are built relatively quickly, often in less than 1 million years, sometimes in mere thousands of years for smaller peaks. But once volcanic activity ceases, erosion begins its patient work. Without continued eruptions to replenish the material, the mountain slowly diminishes. Ancient volcanic mountains, extinct for millions of years, can be eroded down to nearly nothing, leaving only their deeply eroded roots as evidence of their former existence. Yet while they exist, volcanic mountains are spectacular demonstrations of Earth's internal heat and activity. They are direct pipelines from the deep interior to the surface, windows into processes occurring far below. They remind us that our planet is not a cold, dead ball of rock, but a dynamic world still very much geologically alive, with heat from its formation and from ongoing radioactive decay continuing to drive volcanism, to build mountains, and to reshape the surface even as you sleep. From mountains born of fire, we now turn to mountains created by a different mechanism entirely, one involving not compression or volcanism, but tension. We turn to fault block mountains. Fault block mountains, when Earth cracks. Not all mountains form from compression or volcanism. Some arise from extension, from the stretching and breaking of Earth's crust. When rock is pulled apart, it doesn't simply stretch like taffy. Instead, it fractures, breaking along faults, and the resulting blocks can tilt or rise to create mountains with steep, often dramatic faces on one side and gentler slopes on the other. These are fault block mountains, and they represent a fundamentally different mechanism of mountain building. To understand how fault block mountains form, imagine holding a rigid wooden plank and bending it. Initially, the plank might flex slightly, but if you continue bending, it will eventually snap. The same principle applies to Earth's brittle upper crust. When subjected to tensional forces, stretching forces, the crust initially deforms elastically. But beyond a certain point, it fractures, creating faults where blocks of rock can move relative to each other. In regions undergoing extension, normal faults are most common. A normal fault is one where the hanging wall, the block above the fault plane, moves downward relative to the footwall, the block below the fault plane. This downward movement creates space, accommodating the overall stretching of the crust. When multiple normal faults form in a region, they can create a complex landscape of tilted blocks. Some blocks, called horsts, are relatively uplifted, thrust higher as the blocks on either side drop down. These horsts become the mountain ranges. The dropped blocks, called grabens, become the valleys or basins between the mountains. The term graben comes from a German word meaning ditch, while horst means eyrie or eyrie, a fitting name for the elevated blocks. The basin and range province of the western United States provides the classic example of fault block mountain formation. Stretching from eastern California through Nevada and into Utah, this region is characterized by dozens of roughly north-south trending mountain ranges separated by broad, flat valleys. From an airplane, the pattern is striking. Parallel ranges marching across the landscape, each range 10 to 30 kilometers wide and 80 to 160 kilometers long, separated by valleys of similar dimensions. These mountains formed over the past 30 million years or so, as the region underwent significant extension. The crust here has stretched by perhaps 50 to 100%, meaning the region is now 1.5 to 2 times as wide as it once was. As the crust stretched, it broke along countless normal faults, and blocks tilted and dropped. The high-standing horsts, their western faces often steep fault scarps, became the mountain ranges we see today. The Sierra Nevada range of California, one of North America's most impressive mountain ranges, is also fundamentally a fault block mountain, though its story is more complex than a simple tilted block. The Sierra Nevada is essentially an enormous block of granitic rock, the solidified roots of an ancient volcanic arc that existed there around 100 million years ago. Beginning about 10 to 15 million years ago, extensional forces began tilting this massive block westward. The eastern face of the Sierra Nevada is a spectacular fault scarp, rising abruptly from the basins of eastern California and Nevada. Some peaks leap more than 3,000 meters from the valley floor in a nearly vertical rise. Conversely, the western slope of the Sierra Nevada is much gentler, descending gradually toward California's Central Valley. This asymmetry, one steep face and one gentle slope, is characteristic of tilted fault blocks. The steep eastern face represents the fault line where the block broke and tilted upward, while the gentler western slope represents the original top surface of the block, now tilted westward. The process of fault block mountain formation is not always simple or clean. Real faults are complex, often consisting of multiple fractures rather than a single clean break. Blocks don't simply tilt as rigid units. They can break internally into smaller blocks, creating more complex topography. Erosion immediately begins attacking the uplifted blocks, cutting valleys and removing material, which complicates the picture further. And in many cases, volcanism accompanies extension, with magma rising through the fracturing crust to create volcanic mountains superimposed on the fault block topography. The East African Rift, mentioned earlier in the context of volcanic mountains, is also actively developing fault block topography. As the African continent slowly tears apart along the rift, the crust is breaking along normal faults, creating a series of grabens that contain the Great Rift Valley. The shoulders of the rift, the blocks flanking the dropping graben, stand as highlands. Over time, if rifting continues, these features will become more pronounced, potentially creating major mountain ranges flanking a new ocean basin. Fault block mountains, once formed, are subject to the same erosional forces that attack all mountains. Rivers cut through the uplifted blocks, carving canyons and transporting sediment down to the basins below. The basins fill with this sediment, sometimes to great depth, creating a record of the erosion of the adjacent mountains. Over millions of years, the sharp relief between range and basin can be substantially muted as sediment fills the basins and erosion wears down the peaks. Yet the fundamental structure persists. Even ancient fault block mountain ranges, long since inactive, retain their characteristic steep fault scarps, their tilted strata, and their asymmetric profiles. Geologists can recognize ancient examples from hundreds of millions of years ago, their rocks now exposed in regions far from any current tectonic activity, testimony to past periods of extension. Fault block mountains remind us that mountain building is not limited to compression and volcanism. Extensional tectonics can also create dramatic topography, can generate ranges thousands of meters high, can reshape entire regions. The mechanisms are different, the driving forces are different, but the result is the same. Mountains rising from plains, peaks reaching toward the sky, and landscapes of tremendous beauty and complexity. As we contemplate these fractured, tilted blocks, we should remember that the mountains we see at the surface are only part of the story. Beneath them, deeper processes are at work, processes involving heat and pressure, melting and crystallization. We turn our attention now to these hidden forces, to metamorphism and igneous intrusion, and their roles in shaping mountains. The hidden forces, metamorphism and igneous intrusion, the mountains we see at Earth's surface, whether fold mountains, volcanic peaks, or fault blocks, are only the visible expression of deeper processes. Beneath the peaks, hidden from view, rocks are being transformed by heat and pressure. Molten magma is forcing its way through the crust, and the very foundations of the mountains are being forged. These deeper processes, metamorphism and igneous intrusion, are essential parts of mountain building, and understanding them gives us a more complete picture of orogenesis. Let us begin with metamorphism, the transformation of rock through heat and pressure without melting. When rocks are buried deep within a forming mountain range, they experience conditions very different from those at Earth's surface. Temperature increases with depth, rising about 25 to 30 degrees Celsius for every kilometer of burial. Pressure also increases, both from the weight of overlying rock and from tectonic forces compressing the region. Under these conditions, the minerals that make up the rocks become unstable. They don't melt, at least not in most cases, but they recrystallize into new forms better suited to the new conditions. This is regional metamorphism. Metamorphism affecting large areas and caused by tectonic processes. In the core of a mountain range formed by continental collision, rocks may be buried 20, 30, or even 50 kilometers deep, At these depths, temperatures can reach 600 or 700 degrees Celsius, and pressures reach several 100,000 times atmospheric pressure. Original sedimentary rocks like shale and sandstone are transformed into slate, then schist, then gneiss, a sequence of increasingly high-grade metamorphic rocks. Limestone becomes marble. Basalt becomes amphibolite, or, at extreme conditions, eclogite, a very dense rock that can approach the density of the mantle itself. These metamorphic transformations do more than just change the rock's appearance. They affect the rock's physical properties, its strength, its density, its response to stress. The formation of new minerals can release waters and other volatiles trapped in the original rock, and these fluids can migrate, transporting chemical elements and potentially forming ore deposits. The alignment of minerals under directed pressure creates foliation, the layered or banded texture characteristic of many metamorphic rocks. The metamorphic core of a mountain range represents rock that has been to extraordinary depths and then returned to the surface. How does deeply buried rock make this journey? Through a combination of continued tectonic uplift and erosion at the surface. As the mountain range grows, rocks are continually pushed upward, even as those at the surface are being eroded away. Over millions of years, rocks that were once 30 kilometers deep can be exhumed, brought to the surface where we can study them and read their history. Geologists have identified special high-pressure, low-temperature metamorphic rocks called blue schists that form in subduction zones. Here, cool oceanic crust and sediments are dragged down into the mantle, taken to depths of 30 to 40 kilometers before being scraped off the subducting slab and accreted back onto the overriding plate. The rocks metamorphose under the high pressure of deep burial, but remain relatively cool because they descended faster than they could heat up. The resulting blue schist, named for the blue amphibolate minerals that form under these conditions, is direct evidence of subduction. Finding blue schist in a mountain range tells geologists that the region once hosted an active subduction zone. While metamorphism transforms existing rock, igneous intrusion adds new rock from below. Magma generated in the mantle or deep crust rises because it is less dense than the surrounding rock. Much of this magma solidifies before reaching the surface, crystallizing slowly underground to form plutonic igneous rocks. These intrusions come in various sizes and shapes. Small intrusions might be dikes, sheet-like bodies of magma that cut across existing rock layers, or sills, sheet-like bodies that intrude parallel to existing layers. Larger intrusions form plutons, irregular bodies ranging from a few kilometers to tens of kilometers across. The largest intrusions are batholiths, immense masses of plutonic rock, typically granitic, that can span hundreds of kilometers and form the cores of mountain ranges. The Sierra Nevada batholith mentioned earlier in the context of fault block mountains is one such example. This enormous body of granite and related rocks formed between about 120 and 80 million years ago, as magma generated above a subduction zone intruded into the overlying crust. At the time, the Sierra Nevada region was a volcanic arc. similar to the modern Cascades or Andes. Volcanoes erupted at the surface, fed by magma chambers below. Much of the magma never reached the surface, instead solidifying slowly at depth to form the granitic rocks that now make up the core of the range. These plutonic rocks crystallize slowly because they are insulated by kilometers of overlying rock. Slow cooling allows large mineral crystals to grow, giving granite its characteristic coarse-grained texture with visible crystals of quartz, feldspar, and mica. The magma also interacts with the surrounding rock, sometimes melting and incorporating it, sometimes baking it to form contact metamorphic rocks at the margins of the intrusion. The relationship between igneous intrusion and mountain building is complex. The intrusion of magma can provide a kind of thermal and mechanical support to the growing mountain range, adding buoyant material that helps maintain elevation. The heat from intrusions drives metamorphism in the surrounding rocks, and the crystallization of magma releases volatiles that can migrate upward, sometimes causing explosive volcanism at the surface or forming valuable ore deposits as metal-rich fluids precipitate minerals in fractures and cavities. Eventually, erosion removes the overlying rock, exposing these once deeply buried plutonic rocks at the surface. The Sierra Nevada granites, formed at depths of 10 to 20 kilometers or more, now form the dramatic cliffs and domes of Yosemite and other parts of the range. The White Mountains of New Hampshire, the core of the northern Appalachians, are another example exposing granites that intruded during the mountain-building events of hundreds of millions of years ago. Metamorphism and igneous intrusion are thus integral parts of the mountain-building process. They occur at depth, hidden from view, but they shape the character and evolution of the mountain range. The rocks they produce, once exposed by erosion, tell us about the temperatures and pressures reached during orogenesis, about the depths to which rocks were buried, about the magmatic systems that fed ancient volcanoes. They are the hidden infrastructure of mountains, the deeper story written in stone. With an understanding of these hidden processes, we can now consider another agent in the story of mountains, one that doesn't build them, but instead tears them down. We turn to erosion, the great sculptor, the force that begins dismantling mountains almost as soon as they begin to rise. Erosion, the great sculptor. Mountains rise through tectonic forces, through compression, volcanism, and faulting. But from the moment a mountain begins to grow, erosion begins its patient work of wearing it down. Erosion is the great sculptor of mountains, the force that carves valleys, sharpens peaks, and ultimately reduces even the mightiest ranges to gentle hills. Understanding erosion is essential to understanding mountains, because the mountains we see today are not simply the product of uplift. They are the product of an ongoing competition between uplift and erosion, construction and destruction occurring simultaneously. Erosion encompasses multiple processes. Weathering breaks down rock at the surface through chemical and physical means. Chemical weathering involves reactions between rock minerals and water, oxygen or acids in the environment, slowly dissolving or altering the rock. Physical weathering involves the mechanical breakdown of rock without changing its chemical composition, through processes like freeze-thaw cycles, where water seeps into cracks, freezes, expands, and gradually pries the rock apart. Once rock is broken down into smaller pieces, it must be transported away. This is erosion in the stricter sense, the movement of weathered material. Water is the primary agent of erosion in most environments. Rivers carve valleys, carrying sediment from high elevations down to lowlands and ultimately to the sea. Even in arid regions, infrequent but intense rainstorms can cause significant erosion. In cold climates, glaciers are extraordinarily effective erosional agents. A glacier is essentially a river of ice, flowing slowly downslope under its own weight. But unlike water, ice is solid and can carry huge boulders and vast quantities of rock debris within it and at its base. As a glacier flows, it acts like colossal sheets of sandpaper, grinding away the bedrock beneath and plucking blocks of rock from the mountainside. Glacial erosion creates distinctive landforms. U-shaped valleys with flat floors and steep walls, cirques scooped into mountainsides, sharp pyramidal peaks where multiple cirques erode backward into a summit. The Alps, Himalayas, and mountains of Alaska and British Columbia all show extensive evidence of glacial sculpting. During the Ice Ages, when glaciers were more extensive than today, these ranges were heavily glaciated, and much of their current topography reflects this glacial heritage. The Matterhorn in the Alps, that iconic pyramidal peak, owes its dramatic shape to glaciers eroding into the mountain from multiple sides. Wind is a less powerful erosional agent in most mountain environments, though in arid regions it can abrade rock surfaces and transport fine sediment. Gravity itself is a constant force, causing mass wasting events like rockfalls, landslides, and avalanches that move material rapidly from high to low elevations. The rate of erosion depends on many factors: climate, rock type, slope angle, vegetation cover, and the intensity of tectonic activity. Steep slopes erode faster than gentle slopes because gravity works more effectively. Hard, resistant rocks erode more slowly than soft, easily weathered rocks. Wet climates generally see more rapid erosion than dry climates because water is such an effective agent. Vegetation tends to stabilize slopes and reduce erosion, while barren slopes are more vulnerable. Interestingly, erosion can actually influence mountain building through a process involving isostasy. As erosion removes material from a mountain range, the crust becomes lighter, and according to isostatic principles, it rises to compensate, much like a boat rising in the water as cargo is removed. This means that erosion doesn't simply lower mountains, it can actually stimulate continued uplift of the deeper crustal rocks. In actively uplifting mountain ranges, this feedback between erosion and isostatic rebound can prolong the life of the range. The relationship between uplift and erosion determines the ultimate height and longevity of a mountain range. If uplift occurs faster than erosion can remove material, the range grows higher. If erosion keeps pace with uplift, the range maintains a relatively constant elevation, with material being removed at the surface as fast as it is added from below. If erosion exceeds the lift, or if uplift ceases, the range gradually diminishes. Most mountain ranges show evidence of this competition. The Himalayas are currently rising faster than erosion can remove material, at least in some areas, which is why they continue to grow taller. The Appalachians, by contrast, are no longer actively uplifting and have been eroding for hundreds of millions of years. They were once likely as high as the Himalayas, but are now much reduced, their peaks worn down, their valleys filled with sediment. There is a category of mountains called residual mountains, formed not by uplift, but by erosion. In these cases, a region undergoes broad uplift, raising a plateau or wide area to high elevation. Erosion then carves into this upland, removing softer rock and leaving harder, more resistant rock standing as isolated peaks or ridges. Mount Katahdin in Maine is sometimes cited as an example, a resistant granite pluton left standing as surrounding softer rocks were eroded away. The Grand Canyon region of Arizona provides a spectacular example of erosion's power. The Colorado Plateau was uplifted thousands of meters, but rather than creating a mountain range in the traditional sense, the uplift raised a broad, relatively flat plateau. The Colorado River and its tributaries then carved down into this plateau, creating the Grand Canyon and a network of deep gorges. The erosion has been so extensive that some of the peaks in the region are actually lower than the surrounding plateau, existing as remnants of once higher surfaces. Erosion also shapes the detailed form of mountains. Peaks are sharpened by glacial erosion and weathering, creating the dramatic alpine topography beloved by mountaineers. Valleys are carved by rivers and glaciers, their shapes revealing the erosional agent responsible. V-shaped for rivers, U-shaped for glaciers. Landforms like natural arches, hoodoos, and balanced rocks all result from differential erosion, where some parts of a rock mass erode faster than others due to variations in hardness or exposure. The sediment produced by erosion is not wasted. It is transported by rivers to basins and oceans, where it accumulates as new sedimentary rock. In a sense, the mountains of today are being transformed into the sedimentary rock that may, hundreds of millions of years in the future, be incorporated into new mountains in a new orogenic cycle. This is the rock cycle operating on a planetary scale, with mountains as temporary way stations into the endless recycling of Earth's crustal materials. Erosion is not the enemy of mountains, though it eventually defeats them. It is part of their story, shaping their form, determining their lifetime, and redistributing their substance. The interplay between the forces that build mountains and the forces that tear them down creates the complex, beautiful, and ever-changing mountain landscapes we observe today. Having explored fold mountains, volcanic mountains, fault block mountains, and the processes of metamorphism, intrusion, and erosion, we now turn to other mechanisms of mountain formation that don't fit neatly into these categories. We turn to dome mountains and plateau mountains. Dome mountains and plateau mountains. Not all mountains arise from plate collisions, volcanic eruptions, or block faulting. Some form through more subtle mechanisms involving broad, gentle uplift of Earth's crust, sometimes without significant folding or faulting. These are dome mountains and plateau mountains. and while they may lack the dramatic origins of fold or volcanic mountains, they offer insights into other ways Earth's surface can be elevated. Dome mountains form when magma rising from depth pushes up the overlying rock layers without breaking through to the surface. Imagine inflating a balloon beneath a sheet of rubber. The rubber bulges upward, forming a dome. Similarly, when a large body of magma intrudes into the upper crust but solidifies before reaching the surface, it can bow up the overlying sedimentary rock layers into a dome-shaped structure. These domes can be many kilometers across. The overlying sedimentary layers, originally horizontal, are bent into an arched configuration, with the layers dipping away from the central uplift in all directions. Erosion then attacks this dome, removing the softer overlying layers and eventually exposing the harder igneous rock at the core. The result is a mountain or group of mountains with a distinctive structure. A crystalline igneous core surrounded by tilted sedimentary layers. The Black Hills of South Dakota provide an example. This roughly elliptical uplift, about 200 kilometers long and 100 kilometers wide, rises prominently above the surrounding Great Plains. The core of the Black Hills consists of ancient Precambrian rocks, including granite, that were uplifted perhaps 60 to 70 million years ago. Younger sedimentary rocks that once covered the region were arched upward into a dome and have since been partially eroded away, with the harder Precambrian rocks now exposed in the central area. The specific mechanism that uplifted the Black Hills is still debated. It may have been related to the igneous intrusion that formed the granite, or to broader regional tectonic forces. Regardless, the resulting structure is characteristic of dome mountains. A central uplift with layers dipping away on all sides. Plateau mountains, or more accurately, mountains formed by plateau uplift and dissection, represent another category. Here, a large region is uplifted broadly, raising an area to high elevation without creating narrow mountain ranges in the traditional sense. The uplift might result from thermal expansion of the lithosphere due to hot mantle material below, or from crustal thickening through more subtle tectonic processes, or even from changes in the underlying mantle. The result is a plateau, a high, relatively flat surface elevated far above sea level. If this plateau remains intact and undissected, it doesn't really form mountains in the conventional sense, but erosion rarely leaves such surfaces untouched. Rivers begin carving valleys into the plateau, cutting deeper as the land rises, or as they approach lower base levels. Over time, the initially flat or gently rolling plateau becomes deeply incised by canyons. The flat upland surface is reduced to a series of mesas and buttes, isolated, flat-topped remnants of the original plateau, separated by deep valleys. These erosional remnants can appear as mountains, rising abruptly from surrounding lowlands, even though they are essentially the leftover pieces of a once continuous high surface. The Colorado Plateau of the southwestern United States is a spectacular example. This region, covering parts of Colorado, Utah, Arizona, and New Mexico, has been uplifted approximately 2,000 meters over the past 20 million years or so. The mechanism of this uplift is complex and still being studied, possibly involving the removal of dense mantle material from beneath the region, allowing the remaining crust to rise isostatically. The Colorado Plateau's layers of sedimentary rock, originally deposited at or near sea level over hundreds of millions of years, have been carried upward with the plateau. Erosion, primarily by the Colorado River and its tributaries, has carved deeply into this uplifted region. The Grand Canyon is the most famous result, but the entire plateau is cut by a network of canyons with isolated mesas, buttes, and spires standing as remnants of once higher surfaces. Shiprock in New Mexico, a dramatic volcanic neck Mihi. Rising 500 meters above the desert floor, stands as another type of erosional remnant, the solidified magma core of an ancient volcano, with the surrounding softer rock eroded away. The term epiorogeny is sometimes used to describe this type of broad, gentle uplift affecting large areas of continents, as opposed to orogeny, the more intense deformation associated with mountain building at plate boundaries. Epeirogenic uplift doesn't generally involve the intense folding, faulting, and metamorphism of orogeny, but it can raise large areas to significant elevations. The Tibetan Plateau, mentioned earlier as part of the Himalayan collision story, is the highest and largest plateau on Earth, with an average elevation above 4,500 meters and spanning over 2.5 million square kilometers. It formed primarily through the thickening of continental crust during the ongoing collision between India and Asia, so it is fundamentally orogenic in origin. However, the plateau has also experienced more recent epeirogenic style uplift, possibly related to removal of lower lithosphere, raising it even higher. The distinction between different types of mountain formation can become blurred. The Andes, primarily a volcanic arc formed at a subduction zone, also include regions that have undergone significant crustal thickening and plateau formation. The Ethiopian highlands, part of the East African Rift system, combine volcanic construction with rifting and plateau uplift. Nature doesn't always fit neatly into categories, and many mountain regions show evidence of multiple processes operating simultaneously or sequentially. Dome and plateau mountains may lack the dramatic origins of mountains formed at plate boundaries, but they demonstrate the variety of ways Earth's surface can be uplifted. They show that mountain building is not a simple uniform process, but a complex interplay of tectonic forces, magmatic activity, isostatic adjustments, and erosion, all working together to create the diverse array of mountainous landscapes we see across the continents. With these various mechanisms of mountain formation now explored, we can step back and consider how geologists read the history recorded in mountain rocks. We turn to the ancient mountains and what they tell us about Earth's past. Ancient mountains and the rock record. The mountains we see today, impressive as they are, represent only the most recent chapter in a story that has been unfolding for billions of years. Earth has been building mountains for most of its history, and while the mountains themselves rarely survive more than a few 100 million years before being eroded away, the rocks formed during those mountain building events persist. These rocks, now exposed at the surface or buried beneath younger sediments, preserve evidence of ancient orogenies and allow geologists to reconstruct a history of mountain building stretching back through deep time. How do geologists recognize ancient mountain belts when the mountains themselves are long gone? The evidence is written in the rock's structure and composition. Intensely folded and faulted rocks indicate past compressional tectonics. Metamorphic rocks, especially high-grade metamorphic rocks like gneiss and eclogite, show that the rocks were once buried deep within a mountain range where temperatures and pressures were extreme. The presence of certain metamorphic minerals can indicate specific temperature and pressure conditions, allowing geologists to estimate how deeply the rocks were buried. Igneous rocks, particularly large granitic batholiths, suggest the presence of a former volcanic arc and indicate that the region once hosted subduction or continental collision. The age of these igneous intrusions, determined by radiometric dating, tells us when the mountain building event occurred. Unconformities, gaps in the rock record, where older rocks are overlain by much younger rocks with no intervening ages represented, often mark periods of uplift and erosion during which the mountain range stood high and was being worn down. Sedimentary rocks deposited adjacent to ancient mountain belts also tell the story. During active mountain building, erosion strips material from the rising peaks and deposits it in adjacent basins. The resulting sediments are typically coarse-grained, conglomerates and sandstones with large clasts derived from the eroding mountains. These deposits, called molasse in European terminology, accumulate in thick sequences in foreland basins flanking the mountain range. Finding such deposits tells geologists that mountains once stood nearby, even if those mountains have since vanished. The Appalachian Mountains, though still standing as a mountain range, preserve evidence of even more ancient orogenies that occurred before the collision that formed the current mountains. The rocks of the Appalachians include metamorphic and igneous rocks over 1 billion years old, formed during Precambrian mountain building events. These ancient rocks were later incorporated into the Appalachians during the more recent Paleozoic orogenies. By carefully mapping and dating the various rock units, geologists have unraveled a complex history of multiple mountain building episodes, each overprinting and modifying the signatures of earlier events. The concept of the Wilson cycle, named after Canadian geologist J. Tuzo Wilson, describes a repeating sequence of events in mountain building. The cycle begins with rifting, where a continent splits apart, creating a new ocean basin as the fragments drift apart. The ocean basin widens for a time as seafloor spreading continues at a mid-ocean ridge. Eventually, subduction begins at one or both margins of the ocean, leading to the formation of volcanic arcs. Finally, the ocean closes completely as the continents on either side collide, forming a mountain range. This cycle has repeated multiple times throughout Earth's history, with oceans opening and closing, continents splitting and colliding. The Atlantic Ocean, currently widening as the Americas drift away from Europe and Africa, represents a relatively young ocean basin that opened as the supercontinent Pangaea rifted apart starting about 200 million years ago. Before Pangaea, an older ocean called the Iapetus Ocean existed, occupying roughly the same space as the current Atlantic. The closure of the Iapetus Ocean during the Paleozoic era led to the collisions that formed the Appalachian-Caledonian mountain belt, stretching from Alabama through eastern North America, Greenland, Ireland, Britain, and Scandinavia. Even earlier oceans existed in the same general region, their opening and closing leaving fingerprints in even older rocks. Supercontinents appear to form and disperse roughly every 500 to 700 million years, a rhythm driven by the mantle's convection patterns. Each supercontinent assembly involves multiple continental collisions and extensive mountain building. Pangaea was only the most recent supercontinent. Before it came Rodinia, which assembled around 1.0 to 1.3 billion years ago and began to break apart around 750 million years ago. Before Rodinia came older supercontinents like Columbia and possibly others, even earlier, each leaving cryptic evidence in the ancient rocks of continental shields. The Grenville orogeny, which peaked around 1.0 to 1.1 billion years ago, formed mountains during the assembly of Rodinia. The rocks formed during this event, highly metamorphosed and deformed, are now exposed in the Grenville province of eastern Canada, the Adirondack Mountains of New York, and in scattered fragments in other parts of North America and beyond. These rocks, over 1 billion years old, represent the deeply eroded roots of mountains that once may have rivaled at the modern Himalayas in scale. Going even further back, the rocks of ancient continental shields, the stable cratons that form the cores of continents, preserve evidence of mountain building from over 2, even 3 billion years ago. These Precambrian mountain building events, with names like the Algoman, Sphecophenian, and Ebernean orogenes, are harder to interpret because so much time has passed and so much has been eroded or buried. But the evidence is there. Deformed and metamorphosed rocks, ancient thrust faults, granite intrusions. Mountains were being built on Earth when the atmosphere contained little oxygen, when life consisted only of single-celled organisms, when the planet was unrecognizably different from today. Each mountain-building event contributes to the growth of continents. Continents are not permanent, unchanging features. They grow at their margins through the addition of new material during orogenies. Island arcs, oceanic plateaus, and fragments of other continents are scraped off the subducting oceanic crust and accreted onto the continental margin. Over billions of years, this process has built the continents outward from their ancient cores, adding successive belts of rock with each orogenic event. The rock record of ancient mountains thus tells a story of a dynamic Earth, one where continents have drifted across the globe, collided, split apart, and collided again in new configurations. It shows that mountain building is not a recent phenomenon, but a process that has been fundamental to Earth's evolution since plate tectonics began operating, possibly more than 3 billion years ago. And it provides a humbling perspective. The mountains we see today, as grand and permanent as they seem, are merely the latest iteration of a process that will continue long after these current peaks have eroded away. With this deep time perspective, we can now zoom back to look more closely at the history of mountains across Earth's geological timeline. We turn to mountains through deep time. Mountains through deep time. Earth is approximately 4.54 billion years old. For most of that immense span, plate tectonics has been operating in some form, driving the opening and closing of ocean basins, the drifting and collision of continents, and the building of mountains. While the details of early Earth's tectonics are debated, evidence suggests that something resembling modern plate tectonics, or at least its precursor, was operating by 3 billion years ago, or perhaps even earlier. This means that mountains have been forming for most of Earth's history, though the mountains themselves have long since vanished, leaving only their roots and the sedimentary records of their erosion. The earliest Earth, in its first few 100 million years, was likely too hot for plate tectonics as we know it. The planet had just formed from the collision and accretion of countless smaller bodies in the early solar system. The heat generated by these impacts, combined with intense radioactive decay of short-lived isotopes, kept the mantle hotter and the crust thinner and less rigid than today. But as Earth cooled, conditions became favorable for the development of a lithosphere that could break into plates, and for convection patterns in the mantle that could drive those plates. The oldest preserved rocks on Earth, found in a few locations like the Akasta Gneiss in northwestern Canada and the Jack Hills in Western Australia, date to around 4.0 to 4.4 billion years ago. These are metamorphosed and deformed, showing that even in Earth's earliest times, rock was being subjected to high temperatures, pressures, and deformation. Whether this represents mountain building in the modern sense is unclear, but it shows that dynamic processes were already at work. By the Archean Eon, roughly 4.0 to 25 billion years ago, clear evidence of tectonic activity and mountain building appears. The greenstone belts and granite greenstone terrains, characteristic of Archean cratons, show patterns of deformation, metamorphism, and magmatic intrusion consistent with some form of mountain building. The exact tectonic mechanisms may have differed from modern plate tectonics. The hotter mantle of the Archean may have produced more numerous, smaller plates and faster spreading rates. But mountains were being built. Several major orogenies are recognized in the Archean. The Kenoran orogeny, around 2.7 to 2.5 billion years ago, affected much of what is now the Canadian Shield and other Archean cratons worldwide. This event may have involved the amalgamation of smaller cratons into larger continents, essentially an Archean supercontinent assembly. The rocks formed during this time, now deeply eroded and extensively metamorphosed, represent the roots of mountains that stood when Earth was less than half its current age. The Proterozoic Eon, from 2.5 billion to 541 million years ago, saw the continued evolution of plate tectonics and mountain building. During this eon, Earth's atmosphere gradually accumulated oxygen. Life evolved from single-celled to multicellular forms, and continents drifted and collided in patterns that are becoming increasingly well understood as more data is gathered. The Paleo-Proterozoic era, the first part of the Proterozoic, witnessed several major orogenies. The Trans-Hudson orogeny, around 1.8 to 1.9 billion years ago, formed mountains across central North America as several Archean cratons collided to form the core of the continent. The Caecophenian orogeny, roughly contemporaneous, built mountains in what is now Scandinavia and Russia. These events were part of a global mountain-building episode that assembled an early supercontinent, sometimes called Columbia or Nuna. The Meso-Proterozoic era saw the assembly of another supercontinent, Rodinia, through a series of orogenies, culminating around 1.0 to 1.1 billion years ago. The Grenville orogeny, already mentioned, was a key event in this assembly. Mountains formed during this time stretched across vast distances, and the collision was profound enough to produce extensive high-grade metamorphism and massive granite intrusions. The breakup of Rodinia around 750 to 600 million years ago was followed by a fascinating period in Earth's history. Evidence suggests that Earth experienced several severe ice ages during the Cryogenian period, possibly snowball Earth events, where ice sheets extended to the equator and nearly the entire planet was frozen. The mountains of the time would have been ice-covered, and their erosion rates likely changed dramatically. Following these ice ages, life experienced a remarkable diversification, the Ediacaran fauna appearing, followed shortly by the Cambrian explosion of multicellular life. The Phanerozoic Eon, from 541 million years ago to the present, is the interval of time for which we have the best record, both because the rocks are younger and less modified, and because fossil evidence allows detailed correlation and dating of rock sequences. Several major mountain-building episodes occurred during the Phanerozoic, many associated with the assembly and breakup of supercontinents. The Caledonian orogeny, in the Ordovician and Silurian periods, resulted from the collision of smaller continents and microcontinents, leading to the closure of the Iapetus Ocean. This orogeny formed mountains in eastern North America, Greenland, and northwestern Europe. The rocks are now exposed in the Appalachians, the mountains of Scotland and Scandinavia, and elsewhere. The Variscan, or Hercynian, orogeny in the Carboniferous and Permian periods resulted from further collisions as Pangaea assembled. Mountains formed across what is now central and southern Europe, Morocco, and the eastern United States, adding to the Appalachian Belt and forming the European Variscan Ranges. The final assembly of Pangaea was complete by about 300 million years ago. This supercontinent stretched from pole to pole, encompassing virtually all of Earth's continental crust in a single landmass. The interior of Pangaea was far from any ocean, creating extreme continental climates. Mountain ranges lay along the supercontinent's sutures, the zones where continents had collided. But Pangaea did not last. By about 200 million years ago, rifting began as the supercontinent started to break apart. The Atlantic Ocean began to open as the Americas separated from Europe and Africa. The Tethys Ocean, which lay between the northern and southern parts of Pangaea, began to close as Africa and India moved northward toward Europe and Asia. This brings us to the modern era of the mountain building. The collision of India with Asia, beginning around 50 million years ago, formed the Himalayas and continues today. The collision of Africa with Europe formed the Alps and continues to push up mountains in the Mediterranean region. The subduction of oceanic plates beneath the Americas maintains the volcanic activity of the Andes and Cascades. The East African Rift represents the early stages of continental breakup, a process that may, in the distant future, split Africa and create a new ocean basin. Each mountain range, whether forming now or eroded away billions of years ago, represents a chapter in Earth's ongoing story. The rhythm of supercontinent assembly and dispersal, driven by mantle convection, has orchestrated cycles of mountain building throughout Earth's history. Mountains rise, they erode, and new mountains rise in new places. Over billions of years, the process repeats, and yet each iteration is unique, shaped by the specific configurations of continents, the particulars of ocean basin closure, and the character of the tectonic forces involved. The longevity of mountains varies greatly. Young, actively forming ranges like the Himalayas can stand for tens of millions of years, even while still rising. Once tectonic activity ceases, erosion begins winning the battle, and a mountain range may be reduced to gentle hills in 100 to 200 million years, sometimes less if erosion is particularly vigorous. The ancient Canadian Shield, that vast expanse of Precambrian rock forming much of central and eastern Canada, was once mountainous but has been eroded flat over billions of years. What we see now is the deeply eroded root of those ancient mountains, the metamorphosed and intruded core exposed at the surface. This deep-time perspective is humbling. The mountains we consider ancient and eternal have existed for mere moments in Earth's history. The Appalachians, around 480 million years old at their core, have existed for about 10% of Earth's history. The Himalayas, only 50 million years old, are a blink of an eye. And yet, from a human perspective, these mountains are eternal, standing unchanged for all of recorded history, and likely to stand for millions of years more. Mountains, through deep time, remind us that Earth is not a static ball of rock, but a dynamic, evolving planet. The mountains of today will erode, and in the far future, perhaps 100 or 200 million years from now, new mountains will stand in different places, built from different collisions. The processes are timeless, but the mountains themselves are ephemeral, temporary features sculpted by the play of forces both internal and external. As we contemplate this vast sweep of time and change, we can now consider the relationship between mountains and life, how these great landforms shape ecosystems, climate, and human civilization. We turn to mountains and life. Mountains and life. Mountains are more than geological features. They are critical components of Earth's ecosystems and climate systems, and they have profoundly shaped the course of human civilization. From their influence on weather patterns to the unique life forms that inhabit them, from their role as water towers providing fresh water to billions of people, to their cultural and spiritual significance to human societies, as mountains are intimately connected to life on Earth. One of the most significant ways mountains influence life is through their effect on climate. When moisture-laden air masses encounter a mountain range, they are forced to rise. As air rises, it cools, and its capacity to hold moisture decreases. The result is precipitation, rain or snow, on the windward side of the mountain, the side facing the prevailing winds. This orographic precipitation can be heavy, creating lush, wet environments on windward slopes. Once the air passes over the mountain and descends on the leeward side, it warms and dries, having lost much of its moisture. This creates a rain shadow, a region of reduced precipitation on the leeward side. The effect can be dramatic. In Washington state, the western slopes of the Cascade Range receive heavy rainfall, supporting temperate rainforests. But just on the other side, the eastern slopes and interior regions are much drier, almost semi-arid in places. The same pattern occurs on a grander scale with the Himalayas, where the Indian subcontinent receives monsoon rains on the southern slopes, while the Tibetan Plateau to the north is much drier. Mountains also act as barriers to atmospheric circulation, influencing weather patterns over vast areas. The Tibetan Plateau, so massive and elevated, affects the Asian monsoon system. The Andes influence climate patterns across South America. Mountains can split climate zones, creating very different environments on either side of the range. At high elevations, mountains create unique habitats characterized by cold temperatures, intense solar radiation, low air pressure, and often high winds. These alpine environments are harsh, and the organisms that live there must be specially adapted. Trees cannot survive above the tree line, the elevation above which it is too cold or windy for trees to grow. Above this line, alpine tundra dominates with low-growing shrubs, grasses, and wildflowers that bloom briefly during the short growing season. Many mountain species are endemic, found nowhere else because they are adapted to the specific conditions of their particular mountain range. This isolation has been compared to islands. Just as islands in the ocean harbor unique species, mountain ranges act as sky islands, with high elevation habitats isolated from similar habitats in other ranges. If climate warms, these alpine species have nowhere to go. They are already at the top of the mountain. Mountains are also critical sources of fresh water. Snowpack accumulated in winter melts gradually through spring and summer, feeding rivers and streams that flow down to the lowlands. For many regions, especially in arid and semi-arid areas, this mountain-sourced water is essential. The great rivers of Asia, the Ganges, Brahmaputra, Indus, Yellow, and Yangtze, all originate in the Himalayas and Tibetan Plateau. The Colorado River, critical for the southwestern United States, originates in the Rocky Mountains. Mountain glaciers act as long-term water storage, holding precipitation from many years and releasing it gradually. As climate warms and many glaciers shrink or disappear, this water storage is being lost, with potentially serious consequences for downstream populations. The erosion of mountains provides another benefit to life: soil and nutrients. As mountains erode, they release minerals locked in rock. Rivers transport these minerals to lowlands and oceans, providing nutrients that support plant growth and, in the case of the ocean, phytoplankton and the food webs they support. The fertility of many floodplains and deltas is a direct result of sediment and nutrients eroded from upstream mountains. Minerals and metals concentrated in mountains have been critical to human civilization. Many ore deposits form in association with mountain building. As hot, mineral-rich fluids migrate through the crust during metamorphism and igneous intrusion. Gold, silver, copper, lead, zinc, and many other metals are often found in orogenic belts. Human societies have mined mountains for metals for thousands of years, and mountain mining has driven economic development, conflicts, and migrations. Mountains have also served as natural barriers and refuges for human populations. Rugged mountain terrain is difficult to traverse and to conquer militarily, allowing small communities to maintain independence and distinct cultures. The mountain peoples of the Caucasus, the Alps, the Andes, and many other ranges have preserved languages, traditions, and identities distinct from lowland populations. Mountains have also served as places of refuge during times of conflict or persecution. Many cultures regard mountains as sacred, as places where the earthly and divine meet. Mount Olympus in Greece, home of the gods in Greek mythology. Mount Fuji in Japan, sacred in Shinto belief. Mount Kailash in Tibet, sacred to Hindus, Buddhists, Jains, and followers of Bon. Countless other mountains hold spiritual significance. The inaccessibility and majesty of mountains have made them natural focuses for religious devotion and pilgrimage. In modern times, mountains have become important for recreation and tourism. Mountaineering, skiing, hiking, and mountain tourism generate significant economic activity in mountain regions. The first ascent of Mount Everest in 1953 captured global attention, and climbing Everest and other major peaks has since become an industry, though not without controversy regarding environmental impact and the ethics of guided commercial expeditions. Yet, mountains face challenges. Climate change is affecting mountain environments, causing glaciers to retreat, permafrost to thaw, and ecosystems to shift. Species adapted to high elevation cold may be pushed to higher elevations or extirpated entirely. Changes in snowpack and glacial melt patterns affect water availability for downstream populations. Mountain regions are often politically and economically marginalized, and mountain communities may lack resources to adapt to these changes. Mountains, then, are not isolated geological features. They are integral parts of Earth's systems, shaping climate, providing habitats, sourcing rivers, and hosting human communities. The processes that build mountains, operating over millions of years, have profound consequences for life operating over much shorter timescales. Understanding mountains means understanding not just the geology, but the intimate connections between stone, water, air, and life. With this appreciation for the role mountains play in the broader Earth system, we come to the end of our journey. It is time to reflect on what we have learned and to close our exploration gently. Closing reflection. And so, we come to the end of our journey through the formation of mountains. We have traveled from the hidden depths of the mantle, where convection currents drive the motion of tectonic plates, to the highest summits, where ice and wind shape the final details of mountain form. We have witnessed continents colliding with unimaginable force, yet infinitesimal speed, crumpling and thickening the crust to raise peaks thousands of meters into the sky. We have stood beside volcanoes as layer upon layer of lava builds mountains in mere thousands of years. We have watched continents stretch and fracture, creating tilted blocks that become mountain ranges. We have descended into the hot, compressed depths where rock transforms into new forms, and where molten magma crystallizes into granite hearts that will one day be exposed by erosion. We have seen that mountains are not permanent. They rise through processes operating over tens of millions of years, processes driven by heat deep within our planet. They stand for a time, measured in hundreds of millions of years, slowly eroding, their substance carried away by water, ice, and wind to form sediments that may become new rock in distant places. And eventually, given enough time, even the mightiest mountains are worn to nothing, their rocks scattered, their peaks reduced to gentle plains. Yet, as each mountain range erodes away, new mountains rise in other places. The processes that build mountains, the fundamental expressions of Earth's internal heat, and the mechanics of plate tectonics continue unabated. India still pushes into Asia, raising the Himalayas millimeters higher each year. Subduction continues beneath the Americas, feeding magma to the volcanic arcs of the Andes and Cascades. Rifting proceeds in East Africa, stretching the continent and birthing new volcanic mountains. In the future, perhaps 100 or 200 million years from now, the Atlantic Ocean may close, bringing the Americas crashing into Europe and Africa to create new mountains as grand as the Himalayas. Or perhaps other collisions, other configurations we cannot yet predict, will occur. Mountains are records of Earth's history, chapters written in stone and preserved in the rocks that form their cores and flanks. By reading these rocks, geologists can reconstruct the ancient collisions, the long-vanished volcanoes, the seas that opened and closed. Mountains connect us to deep time, to an Earth vastly different from the one we know, yet fundamentally the same in the processes that shape it. You are part of this story, even if you never climb a mountain. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were processed through Earth's geochemical cycles. Cycles intimately connected to mountain building and erosion. Mountains weather and erode, releasing nutrients that feed ecosystems. Mountains capture moisture and store it as snow and ice, providing water for rivers and for life. Mountains shape climates, create habitats, and influence the course of evolution and human history. As you rest tonight, perhaps you can carry with you an appreciation for the forces that shape our world. The mountains you see, whether nearby or only in pictures, are transient expressions of a planet that is geologically alive. They rise and fall on timescales so vast that to humans they seem eternal. Yet in the grander sweep of Earth's history, they are brief features, momentary wrinkles on a dynamic, ever-changing surface. If these explorations have brought you peace, if they have offered a gentle way to end your day with wonder rather than worry, consider liking this video and subscribing to the Sleepy Science Society. It helps other curious minds find their way here, one person at a time, seeking the calm that comes from understanding our place in the universe. The mountains will still be there tomorrow, standing as they have for millions of years, waiting patiently to be climbed, or simply admired from a distance. But for now, rest. Let your thoughts settle like sediment at the bottom of a quiet lake. Let the forces of the earth work their slow magic beneath your awareness. And know that in the grand story of mountains, built and destroyed and built again across billions of years, you are here now, in this moment, breathing, thinking, connected to it all. Sleep well, dream softly, and let the mountains stand watch through the night.